a road sign here, okay, with a road sign, you notice that the rods, forces in these rods are acting in different ways. The force in this rod is a tension, okay, and it's quite clear here, isn't it? Tension in rod AC, because it's like it's pulling back, isn't it, to make sure this sign stays in place. Whereas this here is actually a thrust. With a thrust, it's actually a push, right? It's pushing it. So that rod there is sort of pushing at that point A to make sure this sign stays in place, right? So it's not always a tension where it's pulling back. Sometimes we've got a thrust where we're actually pushing to keep it in place so that that sign stays steady there, okay? So I've got my arrow going that way for the thrust there, okay? But of course the arrow then for the tension here will go away from it because it's like pulling it back. Now, to make sure these are different, I'm going to call it, obviously I'll call that maybe T1 and that T2, okay, just to clarify the difference there. And when it comes to a force diagram, okay, we need to have all the forces acting on a point. So the point here, of course, is at A here, because everything is acting at A, isn't it? The tension, the thrust, and of course the weight of this object, all right? But when we have forces in the diagram, we must have the forces coming away from the point, okay? So forces here acting at this point must be going away from it. Now this thrust here is going into the point. So, but what we can do is we can think of that thrust, because it's pushing at that point, we can think of it as an equivalent tension, sort of pulling that way. Okay, so even though it's a thrust pushing up at A, we can sort of think of it as like a tension pulling the opposite way. And what's good is, right there, is that we've got a symmetry, okay? So that angle alpha there will be the same as that angle alpha. So my T2 goes like that. So when I do my actual force diagram then, I've got my T1 going that way, okay? My T2 going that way, okay, with an angle alpha there. And then of course I've got my weight there coming down, and this object is 12 kilograms, so the weight will be 12g. So that enables me then to do my resolving them in the x and y directions, okay. So quite simply then I've got my T2 there, well, because this angle alpha there will be T2 cos alpha this way, T2 sine alpha this way. I've got T1 going that way, and I've got the 12g going this way. Okay, and of course we know it's in equilibrium. Okay, the other thing we know as well is that sine alpha is 0.6. Okay, so I can put 0.6 there. We can also work out cos alpha. Okay, a couple of ways. One way I like to work out is just using the rule. Sine squared plus cos squared is 1. So because I know sine alpha is 0.6, I can square it. Okay, so I get that. Take the 0.6 squared over the other side. So it becomes minus 0.6 squared. And of course then, when you work that out, it's 0.36. So cos squared alpha is 0.64. So cos alpha actually works out to be 0.8. Okay, so this then becomes 0.8 T2. All right, and because the system is in equilibrium, we can basically say now in the x direction, yeah, 0.8 T2 is equal to T1. Okay, right, so 0.8 T2 is equal to T1, and then in the y direction, 0.6 T2 is equal to 12g. Okay, so you've got two equations, 1 and 2. Now straight away then from 2, we can work out T2 to be 12g, which of course is 12 times 9.8, divide by 0.6. Okay, so I've got my calculator on that. It comes out to be 196 newtons, and then all I've got to do is sub it in there, sub into 1. So 0.8 times T2, which is 196, will give me my T1. So the answer times 0.8, and I get 156.8 newtons.